Okay, this is going to go over how to solve a linear programming problem using geometry. So before we've been actually solving linear programming problems using what's called the simplex method, basically putting it into a matrix, row reducing, doing a little bit of mathematics with it, and then optimizing our objective function. Well, in this case, we can, in some cases, we can actually use geometry to figure out how to maximize our objective function or minimize it, whichever one they want to do. And there's actually some constraints on this. And so one of them, the first constraint is you need 3 variables or less. So that's kind of because we as human beings can see like in a 3D environment, which means that we really need 3 variables or less to visually be able to use geometry to really kind of see how this is going to go, right? And that's really the one constraint. The second thing that we're going to need to do is, if you see our constraint here, we have an inequality. And so as you see, I have a Cartesian coordinate graph here, so we're going to be graphing. So to graph an inequality, let's first make it inequality and then come back to the inequality. So if we have this, let's just say we have my 2x plus y is less than or equal to 4. Let's make that inequality. So that's actually just going to be 2x plus y is just equal to 4, right? So let's go and graph that, right? So if we let x equals 0, we let y is going to be equal to 4, will be one of our points. And then another point will be if y is equal to 0, x is going to be equal to 2, okay? So 0, 4, 1, 2, 3, 4, that'll be one of our points. And then 2, 0, right? Cool. So we have a line going. Pretty bad at drawing lines, but just bear with me. Okay, something like that, kind of something along the lines of that. All right, so that's basically our line. Right now, we want to maximize our x and y, and if we remember, different color here. If we remember, z happens to be equal to x plus y. All right, so we want to maximize that function. We want to find where z is the largest number here, right? So one of our constraints tells us that x and y are both greater than or equal to 0, which means that we're going to have an additional constraint on which quadrant this is going to be in. So remember, x is going to be positive, right? So x has to be going this way. Then y has to be positive, so y has to be going this way, which means that we're going to be contained in the first quadrant. Quad. I'll just put quad. First quadrant, right? Cool. So if you remember, for an inequality, to see which side of the line is true, you simply just plug in points and check for the inequality. So let's go and put the most simplest point, which is 0, 0, right? So to check where the inequality is, we're going to have 0, 0, which means that we have 2 times 0 plus 0 is less than or equal to 4. We get that 0 is less than or equal to 4, which is true, right? That's true. So that means that this triangle here is going to be true because we're bounded by x and y both being positive, okay? So to see where our objective function is maximized, you typically want to look at like the corners. So here you have one corner right here, one guy right there, one guy right there, and we got this guy right here. If you remember, 0 is actually an even number, so it does kind of go in, definitely fills that constraint. Anyways, so okay, let me erase this guy real quick. So to see which one of those points, so one of those points are going to maximize our objective function. So if you see here, this point is 0. Oops, let's go back to that guy. Looks like a 9. This point here is 0, 2. This point is 2, 0. And this point is 0, 0. So to figure out which one of these points is going to give us our maximum value for z, we just plug in these points, their x and y points, into this function right here, right? So we get for the origin, we're going to get that z is equal to 0, right? For this guy right here on the x-axis, we're going to get that z is equal to 2. And for the last one, the one on the y-axis, we're going to get that z is equal to 4. Right? So it's not hard to tell that this guy right here is the winner. Right? So that's one way that you can use geometry to solve your linear programming problem. Just remember that you need 3 variables or less in order to do this with. It can get a little bit, it can get more hairy, you have more constraints in there, but this is the main idea.